So see, transformer working principle we have seen in previous lecture, how it transmit electrical energy from primary to secondary with the change in voltage and current, but supply frequency remains constant. It is a static device. It works on Faraday's law of electromagnetic induction. Okay, that one we have seen. E1 and E2. E1 is self-induced EMF in primary winding. E2 is mutually induced EMF in secondary winding. Okay, we have derived the expression for this E1 and E2. E1 is 4.44 F phi m N1 and E2 is 4.44 F phi m N2. If you take the ratio, you will get E2 by E1 is equals to N2 by N1. 1 minute, student mobile data. Shut. Hello, students. Hello.
Yes, ma'am.
हाँ, so
Yes, ma'am.
हाँ, इलेक्ट्रिसिटी गया था तो वाईफाई ये हो गया मेरा, तो अभी मैंने हॉटस्पॉट से ज्वाइन किया है मोबाइल डेटा से. हाँ, ओके. So in previous lecture we have seen transformer. It works on Faraday's law of electromagnetic induction. Expression for E1 and E2 we have derived 4.44 F phi m N1 and 4.44 F phi m N2. If you take the ratio of this, you will get transformation ratio, which is called K. E2 by E1 is equals to N2 by N1. We have seen transformer. It's a constant flux machine. Load on secondary of transformer, you go on increasing from no load condition up to full load condition. What will happen? The moment I2, we know as load go on increasing, I1 and I2 both increases, and that's why power consumption on primary and secondary also increases. So the moment load you increase, the moment I2 increases, phi 2 also will increase, and in same proportion I1 takes additional current to neutralize the effect of this flux phi 2. Okay, so that's why flux in the core always remains constant. Transformer is called as a constant flux machine. Current density you have seen in 12th. So current density, what is the formula? Current per unit area is the current density, isn't it? Similarly, flux density is there. So flux density is flux per unit area. Flux density is denoted by capital letter B. So flux is denoted by symbol phi, and cross-sectional area of the core is capital A. Whatever this magnetic core, you take its cut section, so its cross-sectional area is denoted by A. Flux flowing through this core is phi. So flux per unit area is the flux density. What is the unit for this flux density? Some of you have studied it in 12th. What is the unit for flux density?
Weber per meter square.
Weber per meter.
Very good. Weber per meter square. And it is also called as Tesla, isn't it? Weber per meter square or Tesla. So whenever you want maximum flux density, so it will be maximum flux per unit area. So transformer, it's a constant flux machine. Here you don't put any load across secondary of transformer or go on increasing load from no load up to full load condition. Flux in the core remains constant. So if flux is constant here, so maximum value of flux will also be constant. And once you manufacture the transformer, what's about core cross-sectional area? That also remains constant. Means what we can say, flux density in the core of a transformer is constant or not? Constant. Okay, because transformer, it's a constant flux machine. Flux in the core remains constant from no load to full load condition. Cross-sectional area of the core is also constant. So flux per unit area, that is the flux density, is also constant. Okay, so here load, you go on changing from no load to full load condition, flux in the core remains constant, flux density of the core is constant. Okay, but whenever I say flux in the core remains constant, in which condition? When the supply voltage is constant. Okay, and that is the case practically. Supply voltage, this one is always constant, but if you change this one voltage, supply voltage, suppose I am changing, then current also will change, then this flux will change, isn't it? Then in that proportion flux density also will change. Okay, but practically V1 is constant everywhere, and that's why phi also constant. So transformer, it's a constant flux machine. Now why rating of transformer is given in kVA? This one part also I think we have finished in previous lecture. For motor, all of you know what is the input. For motor, whenever you switch on any fan, what input you give? Electrical input, and fan rotates, means inside it whatever is the motor, electrical is the input and mechanical is the output. Okay, for that, so formula for active power we know, VI cos phi, formula for power. So for motor, electrical is the input and mechanical is the output. So motor itself is a load. Okay, motor it's here you can see formula for active power, VI cos phi. For motor, electrical is the input, mechanical is the output. So motor itself is a load. So once motor get manufactured, it's cos phi, no, its voltage range, current range also known. That's why if you see the motor, its nameplate, you can find on its nameplate, its specification is given in kilowatt or HP. HP you can convert into watt. Okay, so that specification you can find in given in watt or kilowatt. 1 HP motor or 5 kilowatt motor, isn't it like this? But if you see motor and if you see transformer and generator, on it load continuously changes, because at your home you continuously make on and off load, isn't it? Everywhere in industry, institute. So load on transformer and generator continuously changes. So cos phi is unknown. That's why rating of transformer and generator is given only in volt amperes. Okay, V into I, because cos phi load on it is continuously changing. That is not fixed. But once transformer get manufactured, its voltage range, current range is known for generator also. Okay, now kVA rating, whatever the transformer you will be using for fifth experiment to perform practical direct loading method, it is having the specification 1 kVA transformer. Okay, 1 kVA 110 volts / 220 volt. So 1 kVA transformer, whenever on the nameplate like this is written, we'll show you 1 minute. Or 1 minute, here also I have written specification of transformer. See like this. If you see transformer, it is not open, it is covered with outer metallic box, outer metallic tank, and that on that outer metallic tank you can find one rectangular shape nameplate. On this nameplate, like this specification you can find, see like this. Its kVA rating is mentioned on it, how much maximum voltage you can apply on primary, and how much maximum voltage you will get across secondary, that is also mentioned. Then whether it is a single phase or 3-phase, that is also given. It works at what frequency? All transformers in India works on 50 hertz. Okay, so like the specifications given. kVA rating, whatever the kVA rating given, this one is the transformer specification, which one you are using for fifth experiment. 1 kVA transformer, 110 volt maximum voltage you can apply across primary, 220 volt maximum you will get across secondary, single phase 50 hertz transformer. Okay, so single phase means what? One winding on primary, one winding on secondary, with N1 turns on primary, with N2 turns on secondary. Okay, and whatever the input voltage across primary you are going to apply whatever the secondary side voltage you will get. Frequency is same 50 hertz. Okay. Now here whatever on the nameplate given to you 1 kVA, it is called as full load kVA rating. It is called as full load kVA rating. kVA rating is what? Product of voltage range into current range, isn't it? V into I. Now what we have seen, as load on transformer you go on increasing, what happens with I1 and I2? Does it remain constant or increases or decreases? I1 and I2 with the increase in load?
I1 decreases.
I1.
It's not so. See, last time also I told you. See here again, will tell you. Suppose here you are increasing the load on transformer. Increased load require more power or less power? Each and every lamp is of 100 watt. First lamp, second lamp, third lamp, fourth lamp, and so on. Suppose 10 lamps. Initially 1 lamp, 2 lamp, 3 lamp, 4 on, so on up to 10 lamps. Each and every lamp is of 100 watt. So increased load will require increased power or less power?
Increase power.
Obviously increased power. What's about V1, E1 and E2? All voltages are constant. Constant. Very good. Okay. All voltages are constant. Increased load require increased power. So how transformer will supply increased power to increased load? Cos phi is not in our hand. Cos phi, it's a load power factor. Load power factor it is. So how transformer will supply increased power to increase load? P is equals to VI cos phi. Cos phi is not in our hand. That is the load power factor. Voltages, all voltages are constant. Means which one parameter left?
Current.
Current only. So how transformer will supply increased power to increase load?
By increasing the current.
Very good. Okay, because we have seen on secondary side, load we connect in parallel, total load resistance decreases. This voltage is constant, resistance is decreasing. So I2 obviously increases. And as I2 increases, I1 also increases. And that's why the flux in the core is constant. Means what is the conclusion? As load on transformer, you go on increasing, I1, I2 both increases. I means what's about the kVA rating for every load? Is it constant or changing? kVA rating is what? Voltage range into current range. As you change load, current changes, means kVA rating also changes. Very good. Okay, kVA rating also changes. Okay, so on the nameplate, whenever it is given like this specifications, so whatever the kVA rating you find on nameplate, it is nothing but it is a full load kVA rating. Suppose load is 50% or 60% or 75%, then that time current will be different. So kVA rating also will be different. Got the thing? Whatever the kVA rating you can see on the nameplate, that is called as full load kVA rating. What does it mean? To this full load kVA rating, if I divide by primary side voltage, you will get full load current on primary side. Similarly, to this kVA rating, if you divide secondary side voltage, whatever you get maximum, to this you divide, you will get full load current on secondary side, isn't it? So see here formula, kVA rating, K means 10 to the power 3. That's why here into 10 to the power 3 is there. Okay. So 1 kVA transformer. So 1 into 10 to the power 3 divided by V1. If I do 110 volt, you will get full load current. But for that, kVA rating and this voltage value you have to take from nameplate only. Okay, full load kVA rating, maximum how much voltage you can apply across primary, maximum how much voltage you will get across secondary, isn't it? So how much full load current you are getting for this transformer?
9.09.
Correct, 9.09 ampere you are getting primary side full load current. Okay, now see the secondary side full load current, see here. Similarly, 1 kVA rating is the full load kVA rating, isn't it? And on nameplate you can find secondary side voltage 220 volt. So kVA rating into 10 to the power 3 divided by V2, if you do, you will get full load secondary winding current. And that will be how much you will get here, 4.545 ampere. Now what is its significance? I1 full load and I2 full load you can calculate using the values given on the nameplate specifications, kVA rating, V1 and V2. Okay, use this value to calculate the I1 full load and I2 full load. Now I got I1 full load 9.09 ampere, I2 full load I got 4.545 ampere. Now as you go on increasing load on transformer, we know I1 and I2 value increases. So how much load you have to put on transformer so that current in primary should not be more than 9.09 ampere and current in secondary should not be more than 4.545 ampere. You continuously go on increasing the load, and if you find I1 and I2 value, either both or any one, if reaches to this limit, then do not further put load on transformer. Otherwise, what will happen? Yes, if current through primary winding I am passing beyond this value and current through secondary winding I am passing beyond this value, what will happen with the windings? Primary winding made up of copper, secondary winding made up of copper, both are insulated with some insulating material. So what will happen with these windings? It will burn, and replacement of cost of transformer is repairing cost. Windings you have to replace is very means increases, costing increases. Okay, so never overload the transformer. So for that, what you can do, ammeter you connect on primary side, ammeter you can connect on secondary side and check the current flowing through primary and flowing through secondary. If you find current in primary, in secondary beyond this value, or any one value is beyond this, immediately minimize the load. Okay, so that the current will not be more than this value. Got it? Significance of I1 full load and I2 full load clear? Okay.
Yes, ma'am.
So I1 full load and I2 full load you can calculate from specifications given on the nameplate. Okay. Now next is this is about numericals. You will get asked on this formula. So kVA rating into 10 to the power 3 is V1 I1 is equals to V2 I2. Primary side you can see here, primary side voltage and current, its product, and secondary side voltage and current, its product is equal to kVA rating. So as you go on changing load, I1 I2 changes, so kVA rating for every load is different. Now if I take the ratio of V2 by V1, what I'll get? I1 by I2. So transformation ratio we have seen. We derive the expression for E2 and E1, and if I take the ratio E2 by E1, I'll get N2 by N1, which is called as capital K transformation ratio, isn't it? Now this is the formula, whatever I have circled you can use for both the conditions, at no load also and under loaded condition also for transformer. Okay, now what we have seen, when the transformer is at no load condition, when the transformer is at no load condition, what we have seen, I2 is, when transformer is at no load condition, I2 is, ट्रांसफॉर्मर नो लोड पे है मीन सेकेंडरी ओपन है तो I2 की वैल्यू क्या रहेगी? 0. So what we got, if I2 is 0, what is the relationship between E2 and V2?
Same.
Equals to
Equal. Okay, will be equal. And if the transformer is at no load condition, whatever the current flowing through primary is minimum or maximum?
Minimum.
Minimum. Very good. It is minimum. So you can neglect this I1 R1 drop. If you are neglecting at no load condition, what we got? V1 is equals to E1, isn't it? Means what is the conclusion? When the transformer, it is under loaded condition, use this equation. When the no load is there on transformer, use this equations, isn't it? So what, see, at no load condition, what is the case? E2 is equals to V2, E1 is equals to V1. So whatever the transformation ratio formula, this one you can use for both the condition, under loaded and under no load also. But when the transformer is at no load, when secondary is open, E2 will be equal to V2 and E1 is equals to V1. And what is V2 by V1 is I1 by I2. So when the transformer is at no load condition, you can use this formula. K is equals to E2 by E1 is equals to N2 by N1 is equals to V2 by V1 is equals to I1 plus, is equals to I1 by I2, isn't it? But when the transformer is there, some load is there on transformer, you can't say E2 is equals to V2 or and E1 is equals to V, isn't it? Okay, got the thing? Everyone clear? Okay. When we take the numerical, it will be more clear to you.
Yes, ma'am.
Whenever in your syllabus, whatever the sum you will get asked based on these formulas, mostly it is given that the transformer is on no load condition. So directly you have to use this one. I'll take the numerical, then it will be clear to you. Okay. So this is about the KVA rating. Now, one more thing is there. First of all, losses we'll see. Losses of a transformer. Now see, transformer, two important part is there. One is core, another is winding. Now windings are made up of what? Primary and secondary winding are made up of what?
Copper.
Copper. So correct, copper. If you pass current through them, copper loss will take place, isn't it? So one of the loss which takes place in the transformer is a copper loss, which takes place in primary and secondary winding. Okay. So primary and secondary winding current flowing is what? Which symbol we use to denote the current flowing through primary and secondary winding? I1, I2, isn't it? Current flowing through primary winding I1, current flowing through secondary winding is I2. What's about the resistance?
R1, R2.
R1, R2. So what will be the copper loss on primary side? I1 square R1. What will be the copper loss on secondary side? I2 square R2, isn't it? Okay. So what will be the total copper loss which takes place in transformer? I1 square R1 plus I2 square R2. Got it? Now what we have seen, as load on transformer, you go on increasing. What happens with I1 and I2? Constant, increases, decreases?
Increases.
Increases. See here, as you go on increasing the load, number of times I told you up till now 2-3 times. I1, I2 how increases, that also I explained to you. Okay. So as load increases, I1, I2 increases. Means as load you are changing, I1, I2 changes. So copper loss you will call as constant loss or variable loss?
Variable loss.
Variable loss. Is this clear? So as you go on increasing load, I1, I2 increases, copper loss increases. As you go on decreasing the load, I1, I2 will decrease, copper loss also will decrease. Is this clear? So that's why copper loss is called as variable loss, because it depends on I1 and I2. So how you can minimize this copper loss? Only the option is use copper rather than aluminum. Isn't it? Windings you make of copper, so copper loss automatically will be less. Okay, clear? Now another thing important in, if you see the construction of transformer, another important part is its core, which is made up of which material? Transformer core is made up of which material?
Iron.
Silicon steel. It is made up of which material? Silicon steel. Solid रहती है या laminated?
Laminated.
It's a laminated core. Okay. So it's a laminated core. So whatever the losses which takes place in the core of a transformer is called as core loss or iron loss. Okay. Now Hysteresis loss and eddy current loss it is called. Two types of losses takes place in core of a transformer, eddy current loss and hysteresis loss. Now, what do you mean by hysteresis loss? What do you mean by eddy current loss? How to minimize them? That we'll see. Hysteresis loss. Now, see, we have seen transformer core is made up of silicon steel. And why silicon steel is used to minimize the hysteresis loss? Hysteresis loss means what? See, that magnetic core is made up of material silicon steel and it's a laminated construction. So whatever that silicon steel, each and every plate, you can consider it is a combination of small magnets, and every magnet is having a north and south pole. This is about the core. Core is made up of whatever the material you are using, cast iron, cast steel, silicon steel. So that material, it is nothing but it's a combination of small magnets, and every magnet is having a north and south pole. And whatever the flux flowing through this core is which one? Alternating flux, isn't it? Flux completes its path through the core of a transformer because its relative permeability is very high. And that's why maximum flux completes its path through core only, because it offers less opposition to the flow of flux, isn't it? So whatever the alternating flux flowing through core, as it is alternating flux means what? Its magnitude and direction continuously changes. So what will happen with this all small magnets? They also will continuously align themselves with the changing direction of the flux. So it is alternating, flux is alternating, continuously it is changing the direction. So what will happen with this magnet? These also magnets will continuously align themselves with the changing direction of the flux, and because of this process, whatever the heat produced is called as hysteresis loss. Okay, so hysteresis loss, this is the formula for it. Its derivation not there in your syllabus. First one is called as hysteresis constant. Okay, from material to material, this value will be different. Okay, again, second one, what is the B suffix M?
Flux density.
Very good. Maximum flux density, isn't it? Weber per meter square, Tesla, flux per unit area. Raised to the power 1.67. What is F? What is F here?
Sem-2.
In up till now,
Per
whatever the small f we have used for what parameter?
Frequency.
Frequency. Okay, so here
Frequency.
frequency, whatever is the supply frequency, same will be the frequency of the flux flowing through the core. Okay, and what do you think here? Capital V, it is related to core. So what is it?
Volume.
Volume of core. Okay, so this is the formula for hysteresis loss. Okay, unit is watt. MCQ question you will get asked on this. Which one loss is called as constant, which one loss is called as variable. Whatever the theory part I am teaching, I already told you on each and every parameter, you will get asked the questions. Okay, so KH max to the power 1.67 F into V watt, where KH is the hysteresis constant. This is the maximum flux density, flux per unit area in Weber per meter square or Tesla, supply frequency, same as that of supply frequency, and V here it is the volume of core, and unit for this formula is watt. It's a hysteresis loss in watt. Now, if you observe this formula, KH, it's a constant from material to, for every material, some constant value it is. B, what we have seen, flux density in the core is constant or changing. Supply voltage is always constant. So load, you go on continuously changing on transformer from no load to full load. What happens with flux in the core? Changes or remains constant? Is the transformer remains constant once you manufacture the core? What's about its cross-sectional area of the core
Remains constant.
remains constant. So what will be the flux density in the core?
Remains constant.
Constant. What's about supply frequency?
Constant.
Constant. Once you manufacture the core, what will happen with the volume of core?
Constant.
That also will be constant. Means what is the conclusion? All parameter in this formula are
Constant.
constant. So what do you think? Load on transformer, you continuously go on changing from no load to full load. Hysteresis loss remains
Constant.
constant, provided you are going to keep supply voltage constant. Supply voltage constant, flux will be constant, flux density will be constant. If flux density is constant, hysteresis loss is constant, provided V1 is constant. Okay, and that is the case practically in all application. V1 is constant. Okay, this is about the hysteresis loss. Now this hysteresis loss, how you can minimize it? Obviously every loss should be less, that is expected. So to minimize the hysteresis loss, what is done? This transformer core is made up of silicon steel. Why silicon steel? Because for every magnetic material, silicon steel, cast iron, cast steel, you can plot hysteresis loop. Whatever the graph you can see right now, it is called as hysteresis loop. What is it? It's a H, a B versus H. B along magnetic flux density along y-axis, magnetic field strength H. H is called as magnetic field strength is along x-axis. If you plot this hysteresis loop, see like this it is. It starts from this and then like this behavior you will get for the material. This hysteresis loop not there in your syllabus. This is just for your information. What you have to do, whatever the material for which you have to plot hysteresis loop, take that material in the form of square or rectangular core and round it wound one coil, pass through that coil current in first clockwise direction, then note down some parameters so that you can calculate V and H, then pass the current through that coil in opposite direction. Note down the same parameter so that you can calculate V and H and then plot it. So once you plot, you will get the hysteresis loop like this. Like this, all points you will get and join them together. Like this hysteresis loop you will get. So area under this hysteresis loop is equivalent to hysteresis loss for that material. Okay, so you will find less area for silicon steel. Lesser the area, lesser will be the hysteresis loss. So that's why silicon steel is transformer core is made up of silicon steel, because for silicon steel, whatever the area you will get for hysteresis loop, that will be least. Means what? Hysteresis loss less takes place in silicon steel. And that's why silicon, that core transformer core is made up of silicon steel. For cast iron, cast steel, you will find this area will be more. So more will be the hysteresis loss for these material, isn't it? So how to minimize the hysteresis loss? By using or by manufacturing transformer core of which material? Silicon steel. Okay, that is the case. This is about the hysteresis loss. Which one? Another loss which takes place in transformer core is the eddy current loss. Now, what do you mean by eddy current loss? That we'll see. Eddy current loss. So see here. Eddy current loss means what? This is the formula for eddy current loss. Ke, it's a eddy current constant. This law constant. Then B max, maximum flux density, it's square. Frequency, it's square. And here T is not a time. What is T? It's the thickness of each plate. I told you that core is not a solid, it's a laminated core. Laminated core means what? Like this vertical plates of thickness 0.3 to 0.5 mm get manufactured, number of plates. Similarly, horizontal also of same thickness 0.3 to 0.5 mm. then like this, suppose 20 plates, and then varnish get put on both the sides of these plates. Means varnish is acts as an insulating material, and like this number of plates get stacked together. So like this core get manufactured, means it is a laminated construction and not a solid. Laminated construction, if you are using eddy, current loss will be less. If you are using solid core, then definitely eddy current loss will be more. Now how it happens, see, laminated, if you are using, how eddy current loss get minimized. So whatever this formula you can see, unit for it is not a watt. For earlier one formula, unit was watt, and for this it's a watt per unit volume. Now here also, if you see, this is the constant, B max also constant, supply frequency is constant. Once core get manufactured, thickness of each plate is also constant. So overall, if you observe, all these parameters are constant, means eddy current loss is also constant. Okay, so what exactly eddy current loss? See, we are not talking about the conductor and the flux. We are talking about what? Flux and core. So which one flux is flowing through? Core, silicon core. That transformer core is made up of silicon steel and it is laminated. Okay, and alternating flux is flowing through the core, phi of t, phi m sine of omega t. Its frequency same as that of supply frequency. So alternating flux comes in contact with each and every plate of core. Each and every plate is laminated. It is made up of silicon steel, isn't it? So in core also, as changing flux is coming in contact with each and every plate of core, here also, as per Faraday's law of electromagnetic induction, EMF will get induced in each and every plate of a core. And each and every plate is a closed circuit, and that's why current starts to flow through each and every plate. Now between every adjacent plate, varnish is there. That's why whatever the current flowing through one plate will not flow through adjacent plate. Nothing but what you have done here, cross-sectional area you have minimized. Resistance formula we know, R is equals to rho L by A. We are using here laminated core and not a solid core. Nothing but what you have done, cross-sectional area you have minimized. So if you minimize cross-sectional area, what will happen with resistance of the core? Each
Increases.
it increases. If resistance increases, then whatever this current flowing through the core, that will be
Decreases.
less. That will be less, isn't it? And what is the eddy current loss? I square R. Eddy current flowing through the plate, its square, and resistance of each and every plate of the core. Okay, so here resistance is increasing, but current decreases, and current square is here. That's why resultant overall parameter will be less, isn't it? And that's why eddy current loss will be less. Okay, is this clear to you? How eddy current
Yes.
loss decreases? Because we are using here laminated core. Nothing but you have minimized the area. If you minimize, then resistance of each and every plate will be more to the current flowing through the plate. So resistance is more, that's why current will be less. Here I square is there, and that's why this overall parameter decreases. And if it decreases, then eddy current loss will be less. Okay, so what exactly is eddy current loss? Means what? See, alternating flux comes in contact with each and every plate. As per Faraday's law of electromagnetic induction, EMF will get induced in each and every plate. In each and every plate, it's a closed circuit. So current will start to flow through every plate. When the current, eddy current is flowing through every plate of core, it will offer some opposition. And as eddy current flowing through each and every plate, some opposition will get offered to that, some heat is produced, and that is called as eddy current loss. Okay, so you can minimize it by using the laminated core construction. Clear here? So eddy current loss is also constant. See, all parameters are constant. So eddy current loss also constant. Now here, so means what is the conclusion? Which one is constant loss? Core loss, iron loss is constant, or copper loss is constant in transformer?
Core or iron loss is constant.
Correct. Core loss or iron loss is constant. And why it is constant? Because V1 is constant.
Constant.
V1 is constant, that's why flux is constant, and that's why eddy current loss and hysteresis loss is constant. Okay. MCQ question, which one is constant loss, which one is variable loss? So which one is variable loss?
Copper loss.
Copper loss, because as you increase load, I1 I2 increases, that's why I1 square R1 plus I2 square I2 will increase. Okay, same case will happen with when you decrease the load, reverse things, and that's why copper loss is called as variable loss. How you can minimize it? By making transformer windings of copper. Now which one is constant loss, iron loss or core loss? Two types are there, hysteresis loss and eddy current loss. Both the losses are constant. How you can minimize hysteresis loss? By using silicon steel. How you can minimize eddy current loss? By using laminated core rather than solid core. What are the formula for hysteresis loss? What is the formula for eddy current loss? Keep it in your mind. Because based on formula also questions are there. Which one is the correct formula? Okay. Is this clear about the losses?
Yes, ma'am.
Yes, ma'am.
Now, can you tell me, out of these two losses, which one depends on voltage and which one depends on current? Which loss depends on
Iron
current?
loss. Copper loss.
Correct. Copper loss depends on current. Which loss depends on voltage?
Iron or core loss depend on voltage.
Voltage, because I told you as voltage is constant, flux is constant, and that's why we can say hysteresis and eddy current loss is constant. If you change supply voltage, flux in the core will change, flux density in the core will change, then accordingly eddy current and hysteresis loss also will change, isn't it? But practically as V is constant, core loss is constant, isn't it? Means what is the conclusion? Copper loss depends on current, and core loss, that is the iron loss, depends on voltage. And this is also the another reason why kVA rating of a transformer is given in volt amperes and not in kilowatt. Okay, one of the reason I told you that two reasons are there why rating of transformer is given in kVA and not in kilowatt. Because I told you one reason, load on transformer continuously changes, that's why cos phi is not fixed, and its voltage range, current range is known, and that's why its rating is given in volt amperes. Another reason is whatever the losses which takes place in transformer, copper loss depends on current, core loss depends on voltage, and that's why rating of transformer is given in kVA and not in kilowatt. Okay, so this is about the losses and kVA rating of the transformer. Next, two types of transformers are there from construction point of view. It can be core type or shell type, and one more is there, bale type. Now, mostly these two are used. If you see from generation up to distribution, either the transformers are used from generation up to distribution to step up or to step down the voltage. So either it is of shell type or it is of core type. Now, what is the difference? All of you can see in diagram. Up till now, what I have shown to all of you, if you observe this construction, क्या दिख रहा है यहाँ पे? Separately, I have shown primary winding on left side limb and secondary winding completely on a right hand side limb. Like this construction is used only to explain the working principle and all theory part of a transformer. Like this is not the practical construction. Here what you can see, primary winding only on one side limb, secondary winding only on another side limb. This is not the case. On both the side limbs you can find in construction both the windings are wound. Means on left side limb also you can find primary and secondary winding turns, and on right hand side limb also you can find primary and secondary turns. Okay, so based on this that one construction is called as core type of transformer. See, core type of transformer. Two side limbs, it is having left and right, isn't it? And both the turns are wound on both the side limbs. Core type. What's about the shell type? See here, it is having third one limb also, which is called as central limb. Along with two side limbs, you can find it is having the central limb also, and where the both the turns are wound. ब्लू और रेड में मैंने प्राइमरी और सेकेंडरी वाइंडिंग वाउंड किया है, यहाँ पे दिखाया है. So in shell type construction, can you tell me where both the windings are wound? Are they wound on two side limbs or only on central limb?
Only on central.
Very good.
Only on
They are
central.
wound on only on central limb. That is the difference between core type and shell type. Okay. So here I have used HV and LV terms. LV means low voltage, HV means high voltage. Whenever I say, suppose it's a 110 volt slash 220 volt transformer, means out of these, which one is low voltage? Primary or secondary?
Primary.
Low. Huh, right. Primary is LV and secondary is HV. Okay, like this. So LV and HV. Low voltage and high voltage. Blue I have denoted with low voltage, red I have denoted with high voltage. So near to core in both the construction you will find LV is there, because lesser the voltage, less thickness of insulation it requires. More the voltage, more thickness of insulation is required, and that's why near to core is always LV and above it is HV. In both the cases you can find. LV with blue, and near to core all of you can see initially blue winding is there, that is LV. So what is done? See, suppose it's a core type. तो क्या करते हैं पहले? LV turns. I have started from here. Suppose from A end I have started LV. Then up to this the turns I'll wound. Then the same it continues. Another side limb also. LV turns first, then once LV over HV. Above it, initially from top to bottom on both the side limbs, LV turns. Then above it, HV. See here, HV above it. Then it will come to continue to another limb also, HV. Then above it again LV. Then above it again HV, so on. Here I have shown only 2 layers, but it can be 3, 4, 5 layers depending on how many turns are there. Isn't it? Okay, so initially on both the side limbs LV turns, and then above it HV, then again above it LV, then again above it HV. But you will find whatever the 2 LV turns, suppose ये यहाँ पे एक गलती से मैंने नीचे नहीं ड्रॉ किया है, so ये LV का A है और ये LV का B है. So from A up to B, LV winding is continuous. Similarly, C and D. So from C से start होती है and it is having many turns. Few turns on LV, few turns on HV, number of layers are there. So, but it starts from C and it ends up to D. So, few hundred turns can be there, few thousand turns can be there. Okay. So, like this, if the construction, then that is called as core type of transformer. What's about shell type of transformer? You can see here. This is by mistake I have shown drawn like this. इसमें क्या रहता है? See. LV यहाँ से स्टार्ट हुआ सपोज, सो यहाँ पे पहले रहेगी सपोज नियर टू कोर सेंट्रल लिंब पे 10 टर्न्स ऑफ LV वाइंडिंग, एंड लोअर में भी 10 टर्न्स ऑफ LV वाइंडिंग. देन HV वाइंडिंग टर्न्स, सपोज 20 HV वाइंडिंग टर्न्स, देन अगेन 10 टर्न्स ऑफ LV, then again 20 turns of HV, then again 10 turns of LV, so on. So sandwich between, जो मैंने ड्रॉ किया है that is wrong actually, by mistake I have drawn it. अभी जो मैंने corrected ड्रॉ किया है, so light blue color में जो है वो LV turn है, और जो बीच में black portion है that will be HV turns. Suppose these are the 10 turns, this is 10, 10 टर्न्स, देन यहाँ पे जो है वो कंसिडर करो 20 टर्न्स of HV and so on. So you can find that 20 turns sandwich between 10 turns of LV winding. So sandwich type of wiring arrangement is used here, and that is the construction in shell type. Both the windings are wound only on central lean, and here both the windings are wound on side lean. No central lean is there. Now what will happen with shell type of construction? So this is called as sandwich type of wiring arrangement, and this one is called as concentric cylindrical type of wiring arrangement. Okay, now here what is happening in shell type? Both the turns are wound on central limb only.